All right, good morning, everyone. Let's get started with today's class. If you're online, make sure you turn on your cameras and we'll get started here. Today my plan is for us to finish that exercise. And so if you just go and launch that RStudio project for multivar, that's the one we were working with. We're just going to continue that and hopefully finish that exercise by today. And then next week, we'll officially start with machine learning. So uh, getting closer to that. All right, so if you have your project launched, as always, make sure you have the correct project by checking that top right project name right there. And myself, I don't have any variables on my environment right now, so I'm going to basically run all above. So I believe that we just close this. I believe we've stopped here, right? On this plot. So let me just run all above. So I am on the ED. If you're looking on the table of contents here on the outline, I am under EDA on the second chunk correlation matrix plot. I'm just gonna run all above here. So I get those objects created. And then I'm gonna run this chunk that has that we create that huge correlation matrix plot that really in R is very difficult to make sense. So that's why we export it to file with ggSave. And then we can, on the output, we can check here those correlations in more detail and really look into what's going on a little bit closer. So we were inspecting here, we see that if we take, so this is basically a matrix that has all the variables, all of our weather variables and strength on the y-axis and the same variables again on the x-axis, meaning that you don't really need both sides of this matrix to show up because it would just be a mirror of each other. That's why it only shows half of the matrix. And then basically we can use color here to help us understand a little bit better those correlations. So this is the correlation coefficient, which is R, right? So it's not R squared. One of the differences here is that R is going to be ranging from -1 to 1. So if you were to zoom in on this scale here, you would see that -1 to 1. If it is less than 0, then it's a negative correlation between whatever two pairs of variables you're looking into this matrix. If it is larger than 1, then it's a positive correlation, meaning that when one variable increases, the other also increases. If it's a negative correlation coefficient, as one variable increases, the other decreases. So we can kind of, just we can take a look at that and just make sure that we understand that while if we look for strength specifically, which we did last class, so strength is right here, is this variable. Let's see if I can zoom in. So strength is right here. So if we were just to go up that column, you would see that the R values for the correlation of any single weather variable with strength is pretty low. I think the highest absolute value that we see here is 0.2. So not a very high correlation. And this is perhaps the reason why we're going to do multivariate analysis. So we're going to combine multiple weather variables and see if that improves the single variable correlation that we see with strength. But also something else that's interesting to notice here is there are some very, very high correlation coefficients here. So there's a lot of 1s, 0.9s, -1s, -0.9, -0.8. So meaning that between those weather variables, they're highly correlated weather variables, which makes sense, right? So if you think of it, so if you just, it's kind of hard to take one pair here, but maybe let's try this one, -1. So this is basically mean day length in September. If I look at this -1, and then if we go on this side, that is correlated with mean day length in March. So mean day length in September and March are highly correlated. So a lot of these variables here, you would expect them to be highly correlated, either because it's the same variable, just different months, or because are two variables that are correlated. So perhaps, on a really hot day, you would imagine that your maximum temperature and your minimum temperature both are going to be higher. So that also correlates as well. So we see here that there's a lot of highly correlated predictor variables, and that's important to note because that could cause some issues, which we're going to explore in a second here. All right, so I left you the code here of basically I'm starting with weather, removing site and year, calculating all the potential pairwise correlations, which is what we did above, transforming that into a data frame. If we do that up until here, you're going to see that sometimes you get data frames in R where there are row names. This is not very common. I don't think we've seen in this class before, but right now, if you check this first column, I guess, it's not really a column. It's just the row names, meaning that they're not their own column. They're just the names of the rows. So, and I normally don't really use this format. I prefer to have these row names to be transformed into an actual column, which is what this next function does. So row names to column makes those row names become a column, which right now is called row name. Then I'm pivoting longer, filtering only the absolute values of the correlation that are greater than 0.85 and different than 1. The reason for that is because a lot of the correlations that are equal to 1 is just that variable with itself. So that is not really useful for us. Then I'm arranging on a descending order of correlation and just keeping the distinct values of correlation. So all this basically just to filter the highest correlations in this data set. So if you just run that chunk and if you want to play more with this chunk, you can do that on your side. But basically that's what it's doing. So we see here, for example, the highest correlation of two different variables in this data frame is an R value of 0.999, and that pair of variables is day length in January and day length in December. I guess it makes sense, right? You would imagine that, especially the same variable in 2 months that are consecutive, would be highly correlated. So we see here that there's a lot of highly correlated pairs of variables among our weather variables. And this is something that we need to address in some analysis, but we'll see how we can address that. Similarly, I want to check the lowest correlations or the lowest correlated pairs of variables, which is the next chunk. So I left you the same code. The difference here is just that we're filtering the absolute correlation values that are less than 0.05 instead of the ones that are above 0.85 on the highest chunk that we just did above. So if you go ahead and run the lowest correlated variables, just to explore, we're going to see that the R values are very low and are things that perhaps the variable it's set, there are going to be two different pairs of variables. So the lowest correlated variable we see here is day length in April and precipitation in October. I guess at least, I'm not a climatologist, but I would imagine that there is not a good reason that these two variables would be correlated. So it makes sense that they're not, right? So how much rain you get in October with day length in April, very low correlation between those two pairs of variables and so on. So we have, again, 73 variables, weather-related variables. Some of them in a pairwise correlation are highly correlated. Some of them are not. So basically, this is something that I wanted us to understand because as we move through this exercise, we're going to see a simplistic example of the implications of running models with highly correlated predictor variables, which is what is going to come next. On this next chunk here, I basically left you the code as well, but basically I want to understand the correlations specifically with strength. So on the chunks above, I did not specify, I was just looking for strength. I was telling me, show me the highest correlated variables in a pairwise format, whichever variables they are. I didn't specify, I wanted to only look at strength being one of the variables. Now in the next chunk, we are doing that. So basically, let me show you here what this code is doing, just kind of walking you through, starting with weather, removing side and near, pivoting longer, everything except strength, and then grouping by and nesting. So if you just run until that nest, this is what you would see, that for each one of our 72 weather variables, we have a new data frame. If you were to pull that data frame, this would basically have the weather variables or the weather values for each one of those variables and strength. So we have that variable and strength for each one of these tables under the data column. Then I'm doing a mutate with a map. In this case, map double. It's another type of function from the map family of functions. The main difference is that map returns you any object. Map double returns you a double, returns you a number. And this number, if you just follow here, I'm basically running a linear model with strength explained by value, where value is each one of those weather variables. Then I'm piping that right through a function called glance. You know what? Let me actually assign this to an object so I can show you what is going on here. So let me just call this, I don't know, test. Just, I don't even want to keep this name after it, just so I can break this down a little bit more for you. So if we print test, it basically has a column for R squared, which is what I wanted to extract from the coefficient of determination, which is R squared. Coefficient of correlation is R, coefficient of determination is R squared, even though we refer a lot of times to R squared as referring to a correlation analysis. So it could be a little bit confusing. But anyways, so here I'm basically running a regression of strength explained by each one of these weather variables. The function glance pretty much extracts model fit metrics from any model. And then I'm piping that result of glance into pull. So let me perhaps do this on one case, just so you see a little bit better what this looks like. So let me take here weather data, oops, not weather, test data 1, which is that first, the first data frame. If I pipe that into an LM with strength detects explained by value. And then I think we need to say data equals dot. Let's see if that works. Okay, that worked. So it just ran that first model for us, like outside of the map function. And I'm gonna pipe this into a function called glance. Glance dots. So glance basically gives you these fit metrics related to that model. So there's R squared, adjusted R squared, sigma, a statistic value, a p-value, degrees of freedom, and number of observations, AAC, BIC, a lot of things about that. So basically fit metrics about that model. You can see that on glance, we have a column called R squared. So I can basically, if we use the function pull, we're basically just only getting that column. So if I do pipe, we're just going to copy from the code above. So pipe pull R squared basically just gives me that number. This is just showing you what this code here on the map function is doing, but here just in one case, so we can break it down and show you the intermediate steps. So basically I'm running a model, getting all the fit metrics using glance and only pulling the R squared from the fit metrics. And that is what is being saved under R squared. That's basically what's doing. All right, I'm going to delete all this because it was just to show you what the mechanics of it. And I'm going to delete the test weather as well, or test object. But if you just run that, basically here we get a column with R squares in descending order of which variable was able to explain fiber strength in going from higher to lower R square. Again, here we're focusing on strength being explained by each one of the variables. And we see that even the best weather variable here was solar radiation in April. It's a pretty low R square, right? So it's not showing us a very high predictive ability when we're using single variables to explain fiber strength. And then here, I'm just making a plot of that. I'm not going to walk you through the whole code, but basically what we just did above is the initial part of this code. And then I'm just taking the 6 highest R squares and showing you the plots that generates, or the scatter plot of which the points and relationships generate that R square. So, because just looking at R square values can be useful for you to just do some rankings, but I always urge you to look at your data, make plots, visualize that, understand why this R square is 0.06, and the worst here is, I mean, I think we're plotting the top 6, so the worst of the top 6 is 0.04. Why is that so? That's what we're doing here. You can play with the code on your side if you want to understand better, but basically just creating the plots. So we have here strength on the y-axis, and we have value on the x-axis, where value we're faceting by the top 6 weather variables that have the top 6 highest R square values with strength. So again, the R square values that we calculated on the chunk before are coming from these relationships that we're observing right here. So this is just a scatter plot with a geom smooth of that relationship. So we see here, for example, that the first 4 panels here, so solar radiation in April, solar radiation in December, solar radiation in February, and solar radiation in July, it looks like the higher you had those solar radiation values on a month, on the average on a monthly basis, the lower strength, fiber strength was. And then vapor pressure deficit in April and precipitation in April were in a positive relationship. So solar radiation seems, at least what we're seeing here, seems that it had a negative effect on strength, whereas vapor pressure and precipitation in April had a positive effect. Now, one thing that's going to be an important point when we're going to get to that point, we didn't get it yet, but I just want to anticipate your thinking. If you're not familiar with growing cotton in Georgia, normally cotton's planted perhaps starting in early May and is harvested maybe like late November is probably what we see a good window of planting and harvesting in Georgia. So between May and November, let's say, let's simplify to that. Why would solar radiation in December be so high? I mean, not highly correlated because it's still a very low correlation, but among the variables that we have is among one of the highest correlations with fiber strength. So solar radiation in December, even February, I mean, the crop is not even planted then. Precipitation and vapor pressure deficit in April perhaps makes more sense because maybe that has to do with like how much water is available in the soil for the crop that's about to be planted, which is going to be in May. But like things that happen in December and February, January, I mean, maybe there is a good explanation for this, but especially solar radiation, I don't know if I can really defend, like, you know, if you create a model where the most important variable, weather variable, is one that happened when the crop was not even growing. I don't know. Maybe there is a reason, but I think it's still a little bit of a stretch, right? So when we get to actually the part of when we start running machine learning models, I will propose that we remove some of these variables, especially the ones that are not really within the growing season of this crop. So we keep variables that from a biological standpoint makes more sense to keep them. Okay, so this point we're going to be talking about multicollinearity. So multicollinearity The definition of that is when more than two explanatory variables, or if you remember, another way of referring to explanatory variables is predictor variables. So our weather variables are examples of that. So when more than two explanatory variables in a multiple regression model are highly linearly related, meaning if you have high correlation between your predictor variables, like we saw solar radiation, or I think it was solar radiation, or day length in December and January, highly correlated. If you put both of those variables in the X side of your formula, you're going to have multicollinearity problems with that model. And why is that an issue? Why do we care about multicollinearity? If you do have multicollinear variables as predictors in your model, the estimates of your model, so the estimates of, for example, the slope or the intercept, the magnitude of those estimates and also the direction, so whether that estimate is positive or negative, meaning do you have a positive relationship or a negative relationship with strength, for example, they can change for multicollinear variables so let's say you run a model where you have two multicollinear variables. The model tells you that one of those variables has a negative relationship with strength. But then you run another model where you do not have multicollinear variables, so their predictors are not correlated. And now instead of having a negative relationship of whatever variable you had with strength, now it's a positive relationship. So how come is the relationship changing just because you have a different set of variables? Well, that's what multicollinearity can do to our models. So whenever we have two or more highly correlated predictor variables in a model, you can have multicollinearity problems. And if that's the case, the estimate magnitude, so even just like, well, strength, how much strength is changing for each unit of solar radiation in a given month, that can be 1 or 10. I'm just making up some numbers, but just the magnitude of that can change if you compare a multicollinear model with a non-multicollinear model. So, if you just think about it, that's bad, right? Because it should not be that way. You should not be having such an impact of how whatever variable is explaining your response variable, in this case, strength, just for it being in a model with another multicollinear variable or not. Also, besides the estimates, magnitude, and direction shifting, your standard errors become very inflated when you have a multicollinear model, meaning that it's going to be more difficult for you to find significant terms or significant p-values in your analysis. So I know that this concept can be a little bit difficult to understand, so I do want to walk you through an example using the data that we're looking at right now. So the first thing that I want to do is just create a scatter plot here with two uncorrelated predictor variables, just so we take a look at them. So I took here mean day length in April and precipitation in October. If we look at the scatter plot of those two variables, this is how that looks like. And then I added the geom smooth here to just add a trend line for us to visualize as well. As you can see, it's pretty much a cloud of points, right? And the geom smooth is really showing you that when you add a trend line, you really don't get much out of this. Meaning that these two predictor variables, well, right now, one of them, in this model at least, in this plot, one of them is X, one of them is Y. But we'll run a model where both of them would be X variables explaining strength to see the effect that they have on strength. So right now, just looking at this pair here of scatter plot between two uncorrelated variables, we can see that precipitation October, day length in April are not correlated. So if they were to be included in a model, we will likely not have multicollinearity issues. In contrast, let's look at the scatter plot of two highly correlated variables. So day length in April and day length in May. If you run this plot, this is what you see. Highly correlated variables, right? You have a high correlation between mean day length in April and mean day length in May. So if you do run a model that you say, for example, strength explained by these two variables, that will likely be a model that will suffer from multicollinearity. because these two predictor variables are highly correlated. Now, I do want to fit some models here to do that, to really go through this very simplistic example for us to create the understanding of how is multicollinearity changing the results of our models, and how that is a problem. So if you come here to the next chunk, we're going to run a model that is basically going to be, yes, Sobir.
Dr. Pastor, I think I'm having an error running the R uncorrelated chunk.
This one here?
Yes.
So what I would check is, because I mean this, if you're having an error here, I gave you the code already. So I don't expect that the code would have a problem unless you made some changes after I shared. So my guess is
I'm also
maybe,
facing the same problem.
So have it errors.
Yeah, I'm also having the same problem.
okay, all right.
Same here.
Yes.
There is one thing that I can share. So I tried to run it line by line. It will run fine till geom smooth, but once you run the stat correlation, that's when I'm getting the error.
Okay. Nice. Thanks,
Yes.
Kumar.
That's true.
So that's so for now, okay, so maybe let me take just a quick moment here and use this moment to show you. So what Umar realized, so if you run a chunk, right, that is either a pipe flow or a ggplot with the pluses, if you run it and you get issues. So I'm just gonna create a new issue for me here. So I changed the function name to something that does not exist. I added an S at the end of that correlation. Maybe the error message is useful. In my case, it is saying could not find function in stack correlations. If that is the case, what this means is either that I forgot to ask you to either install or load a package, the package that has this function, the stack correlation without the S, which on my side, it was loaded, I believe, because I'm not getting this problem. So let me just do a quick help here. Stack correlation, so that is coming from the ggp misc package, which I think is one of the packages that I asked you to install at the beginning. But anyways, I don't want us to spend too much time here. So what I'm gonna do is whenever you run into an issue like that, let me go back to the chunk. That you run something that it's in a pipe flow, and it doesn't work. I believe maybe that's what Omar did, but what I would do is first try to identify what part of the code is giving me the error. So, you know, for example, I would first stop the pipe on the first line of code. I mean, I wouldn't expect to be here because we're just printing, in this case, the weather object. So I run that, no problems. So it means that that's not where the problem is happening. I would go then to the next part of this code, which would basically be adding a hashtag right before the plus at the end of ggplots. I run that. If that goes through without errors, the error is not there. I let it go through that, let the flow continue until the next line. I add a hashtag right before the plus, run it. Okay, no problems, it worked. And I keep doing that until I identify which line of code is really stopping the flow. Because if you have an error somewhere and you run the whole thing, you may not be able to understand where exactly the problem is happening.
From third layer.
From third layer.
Why
What do you mean third layer?
this way. 1, 2, 3.
So on the geom point?
No. Y equals some here.
Oh, here shows it there. Is more people seeing the same?
But it says error in the stack correlation.
Yes.
Okay. Yeah, so I think it was probably something with maybe my version of ggp misc is different than yours if you install last class. So really everything that stat correlation is doing is adding is adding the R value here. So in our case, so we keep moving, I would say just add a comment on the plus after geom smooth and add a comment before stack correlation. So that would run. It's not going to give you the R value in the plot, but that's fine. That was just for an annotation of the plot. But that's how basically you would troubleshoot and see what line of code is giving you the error, and then you can be more focused on trying to solve exactly where the error happened. So Abir, thanks for bringing this up. As we saw, a lot of people were going through the same issue. So thanks for bringing that up, so we could help everyone as well. So again, this stack correlation function comes from the GGP MISC package. Maybe, I don't know, something in that package happened. I don't know if my version is different from yours and your version is newer, and maybe they changed the package, the function name, or what happened. But in any case, I don't want us to get hung up on this specific case because it's not something that is really key here for this plot. Well, I guess, was everyone able to run this chunk here, or was somebody not able to run this chunk after commenting off the plus and the stat correlation? As you expect, you're going to have to do the same on the, well, I guess the next chunk doesn't have it actually, that function, so you don't have to worry about it there. Yeah, so you should be able to run the second chunk of the highly correlated variables, right? Yes. Okay, I just want to double check again that nobody's left behind before we keep moving. Yes, it's not running. Which one?
This says error in whether Finland has the pipe. It says could not find function type.
Yeah, so if you I think you may have forgotten to run your setup chunk. Well, while Minder is helping Jonathan here, anyone else online having issues or not able to run?
I was able to run, but I was trying something out with the, from the help section of the start correlation. I saw an argument called parse. I kind of changed it to false. It ran, but then it's not really writing the label correctly. You can see the label, but it has like italic R, blah, 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 0.01.
But so Comfort, on your side, did it work the first time to use the stack correlation?
No, it didn't work
It didn't.
until I added the parse. Yeah.
Okay, so
Dr. Bastos,
yes.
I tried running it like stat core and not the complete correlation word, and it did work for me. So maybe.
Okay, so let me try that. So Madhuparna is saying she tried stat core. Is that like, I don't have
Yeah,
it.
that's all. I mean, it did run for me.
Okay, so maybe for me, I don't even have that function available. So maybe it is a difference in package version that maybe GGPMISC updated their function names, and maybe you do have, maybe they changed.
Yeah, so I installed a package called ggpubr, and then I ran the stat core and it worked for me.
Okay, so it's coming from a different package. Awesome. All right, well, thanks, Madhuparna. Oh, again, I don't want us to spend a lot of more time here just because it's a very small thing. But I think the one thing that we could take away is that if you have issues on a pipe flow, especially, you can just comment off the pipes and try and identify where is the error. So for now, if that stat correlation was not working for you, just add a pipe before the plus and before the stat correlation, and so we can keep moving. Awesome, but thanks everyone for all the comments and tips as well. All right, so if we continue here, so we just observe a plot of two non-correlated variables and then of two highly correlated variables. And even though in these plots, one of those variables is X, one is Y, when we run models, both of them are going to be on the X side of the equation because they're going to be explaining fiber strength, which is what we're going to do next. So the first model we're going to run here is to use basically just explaining fiber strength with one variable, just a very simple model that's going to be mean day length in April. So if you start coding with me, we're going to start coding here using the function lm to run a regression. Our response variable in this case is going to be strength. So strength underscore gtex explained by just one weather variable. What's going to be mean underscore day L dot S underscore uppercase A PR. So mean day length in seconds in April. If we get a comma, we need to specify our data. So data equals weather. If you want to make sure that you are able to type the correct name with all the dots and underscores and uppercases, you can just go ahead and run this. If it runs, then you typed correctly. If it didn't, then it's going to give you an error. All right, so we just have this regression here result right now. What I want to do is extract the coefficients or the estimates of this model. So we're going to pipe this model here right into a function called tidy. So the function tidy, if you run that and you print the output, it gives you the estimates. So it gives us the intercept, which is the estimate is minus 1.4, and give us the slope. It does not say slope. What it says is the name of the numerical variable for which we had as an explanatory variable here. But this is basically the slope. So this is the amount for which each increase in mean day length in April increases on strength. That's basically what the slope is in any regression. So this tidy here is giving us this slope. I want to basically only keep the second line here. So I do not care to keep the first line related to the intercept because I want to compare the slopes of different models as we keep going. So right after that tidy, I want to give a pipe and do a filter where I want to filter the terms. I could either say I want to filter mean day term equals mean day length, or I can say I want to filter terms different than intercept. I'm going to do that because that's going to be more generalizable as we move to more complex models. So let's just say term different than, which is exclamation equals sign. And then in quotation marks, you can just copy that parentheses, intercept, parentheses. So we only keep the slope of this model. And then finally, I want to create a new column here to give a name to this model because then we're going to make a plot. So let's give a mutate. I want to have this next column called mod to have the model name. And I want to basically say that that's equal to the name of the object. So LM day length in April. So if you run all that, we basically ran a linear model with strength explained by mean day length in April. We got the coefficients on the tidy function. We filtered out the intercept and only kept the slope. And then we gave a name to this model, which is under the column mod. So if you go all the way to the right, you have a column saying mod and then day length in April. Any questions about what we just did? All right. So the next thing is I want to run another model. I left you the code already because it's basically very similar to the previous one. The difference now is that we're running a model explaining strength using another weather variable. So this is sum of precipitation in October. So we're still doing that model, getting the tidy to get the coefficients, filtering the intercept out, and then giving this model a name as well. So this is LM precip in October. if you just run that and you print it, again, we just keep the slope of this model. So the slope between the relationship of strength and precipitation in October. Now I want to run a slightly more complex model on the next chunk. So in this case here, we're explaining strength with two weather variables, day length in April and cumulative precipitation in October, which are the same variables of this plot, where we saw that those predictor variables, both precip in October and day length in April, are not correlated at all, right? So we would expect for this next model here, so strength explained as mean day length in April and precip in October, to not have multicollinearity issues. That's just an assumption based on what we know of these two weather variables. So I'm running that model. Now, if you print, the output has two lines instead of just one, because it has a slope for mean day length in April, and it has a slope for precipitation in October, differently from the previous ones that only had one variable and therefore just one slope. And then we're also giving a name to this model here that is the same name, or in this case is LM, two variables uncore, to mean that it's our two variable model uncorrelated predictors. And next, we want to run a fourth model here, which is going to be explaining strength with mean day length in April and mean day length in May, which are the same two set of variables that we had that plot that was highly correlated. So we would expect now that this fourth model to have multicollinearity issues. That's our expectation based on what we know of those variables. So if you run that chunk, I left you all the code, and we give the name of this model here being LM two variables core, meaning that it's probably, well, we know that those predictor variables are correlated, so we were expecting to have multicollinear problems. All right, so just to recap what we did, we ran 4 models. All of them, the Y variable was strength. What we're changing is the X variable. The first model was strength by mean day length in April by itself. Because there is only one predictor variable, there's no problem of multicollinearity, because multicollinearity is when at least 2 predictors are correlated. In this case, just one predictor, no problem of multicollinearity. So it's strength by mean day length in April. Then we did strength by precipitation in October. The third model, we combine both of those previous variables into one model. So day length in April and precip in October. And we know those 2 variables they have very little correlation between them. So we would expect this model to not suffer from multicollinearity. And then we ran a fourth model that we explain strength with 2 highly correlated predictor variables. So we would expect for this model to suffer from multicollinearity. So my objective with this is now we look into the intercept estimates of all these models. And we look into the models where we saw each one of those weather variables by themselves, and then each one of them in a correlated model, in an uncorrelated model, and see how their estimates, how their slopes are changing. That's the goal. So I think you're going to have to code a little bit with me here. So basically what we're doing is I'm starting with that first model that just had day length in April, and then binding rows with the other 4 model objects. If I just run until the end of bind rows, I just want to show you what that is. We have 6 rows where we have the slope for the first model, the slope for the second model, 2 slopes for the third model, 2 slopes for the fourth model. And we have that column mod name that we can use to make some plots and understand which estimates are coming from each model. I'm just then transforming the mod column to factor because I wanted to have these models in a very specific order. And I am removing the mean day length in May. Because that in itself, that was the last model had mean day length in May. And mean day length in May did not appear in any of the previous models. So for comparison reasons of multicollinearity, we're not going to use that term because it was not present in another model. We are going to compare though mean day length in April. So mean day length in April was in a model by itself, was in a model that we expect to be non-multicollinear, and it was in a model that we expect to be multicollinear. So that's the one we're going to focus to see the effect of multicollinearity at play. And I really like making plots, so we're going to show all this in a plot. So we're piping the results. So if you just run all this until right before you get to ggplots, this is basically the data frame we're giving to ggplots. So what I want to do here is put X or put the model name on the x-axis. I want to use a geom here that maybe you have not, well, at least not in this class. I don't think we've used it. It's called geom underscore point range, which is basically a geom that gives you a point and then a range of some confidence column that we can use here. And that confidence could be different metrics. We're just going to be using the model standard error as that confidence. So here on geom point range, let's call AES. On the Y column, we do want to put the estimate. So that's where the point's going to go. Imagine that you're going to have a point and then a confidence interval around it. The estimate is the point. Now we need to tell it what is determining the upper end of the confidence level on top that goes above the point and the lower end that goes below the point. What I want to do here is basically, so the argument is called ymin. So maybe let's first determine the end of the confidence going lower than the point. So what I want to say here is basically ymin is going to be equal to the estimate minus the standard error. We have a column for standard error. And then Y max is going to be basically estimate plus standard error. We can run now, although I think it's going to look very, very busy because we have not faceted it yet, which we're going to do in a second. But I just wanted to see the effect of point range. So this is what point range does for us. It adds up points and just like a confidence interval of some sort. In this case, that interval is basically plus or minus the standard error of the model. Now let's add a plus. I want to control the let's see, maybe let's go ahead and do a faster rep as the next step. So I want a faster rep by term. So if you remember, the term is what is the slope we're looking at. I'll be with you in a second, Omar. Let me just finish this. And then I also want to say scales equal free underscore y. So the y axis has its values ranging on a free form. So this is what we see. Before we continue, yes, Omar, go ahead.
Yeah, Professor, I was wondering if this geom point range would work same with standard deviation as well.
So standard deviation is not in the unit of the measure of your response variable. You could do it. So really here, the key to understanding point range is you can give whatever type of, so the second part here after estimate could be, I mean, in theory, it could be really any metric, right? It could be any column you have in your data set. You could use standard deviation if you wanted. It's just that standard deviation is normally not in the unit of the measure variable, of the response variable. So it makes a little bit more intuitive sense to do like an estimate point that is in grams per text, and then a standard deviation that is not in that unit. Standard error is in the unit of measure, so it's a little bit more interpretable. But really, there's many types of point range you can do, right? So there's different confidence intervals you can create and show in a plot. So it's really up to the person that's making the plot to decide what they want to use there.
Okay, thanks.
All right. I think the next thing I wanted to do just to make this a little bit better to see is right now the x-axis or the x-axis text is overlapping, so the model names are overlapping. Before we go ahead and interpret this plot, I just want to show you one way that you could fix this. So let's give it a plus. I want to call a function scale underscore x because we're going to be changing something about the x-axis. Underscore discrete because our x-axis is discrete, right? We have names. We have model names in the x-axis. So what I want to say here is we want to call the argument guide. So guide equals to, and then we call the function guide underscore axis. This is a function. So guide is the argument, guide axis is the function. And it has an argument for n dot dodge. I want to say equals to 2. So what this is going to do is basically dodge every other label to be like on top, below, on top, below, on top, below. So now they're not overlapping anymore. We can interpret them. Okay, so now I really want to take a moment to talk about what is going on here. So let's just walk through each one of the models and what we're seeing. I'm basically showing you on these two facets here. One of them is showing you the slope and the error of that slope for models that contain mean day length in April. The other facet is showing you models that contain precipitation in October. If we focus first on mean day length in April, we have 4 models where mean day length in April was present. The first model was when we explained just using, the model was strength explained by mean day length in April. That was it. Only one variable. We see that the slope of that relationship was, so here's the 0 line, just so you visually assess. So that the slope magnitude was greater than 1, so it was a positive relationship. And the error around that is, you can barely see, but there is a little error around that point. The second model here, the LM precip October, that model was just strength explained by precip. We did not have day length in April in that model, so that's why we don't have anything showing up here. The third model was the one that we had both day length and precip in October, which are uncorrelated, explaining strength. This is the second model here. What we see is that the magnitude, so the estimate point of the slope of mean day length in April and the error associated with it are very similar to the model where we only had the mean day length in April by itself. And that's because this model, the second model, or actually the third model that we ran, we had 2 variables explaining strength. It was mean day length in April and precip in October, which are uncorrelated predictors. So this third point here is coming from a multivariate model that does not suffer from multicollinearity because it had 2 non-correlated predictor variables. Now, what happens with the estimate of the effect of mean day length in April and the error associated with that estimate on the last model? So first, again, the 0 line is here. So first, the direction of the relationship between mean day length in April and strength changed. Now, instead of a positive direction, it's a negative direction. Also, the error associated with that estimate of that slope is a lot higher. And that's because on this last model here that we're seeing this information, we ran, the model was strength explained by mean day length in April and mean day length in May or some other month that are highly correlated. So you see that on this highly correlated predictor variable model, this model is suffering from multicollinearity. And this is what happens. You can drastically change your interpretation of your model because you have multicollinearity. And if you're unaware of it, that could be a problem, because I hope you're understanding here that in both alone and when it was in a non-multicollinear model, the effect of day length in April on strength is positive. But if you have mean day length in April with another correlated predictor, the effect of mean day length in April on strength now is opposite, is negative, and you have a lot more uncertainty around it. That's basically what multicollinearity can do to our models and our estimates of the model, and in the end of the interpretations you make of that relationship. So multicollinearity can be a really important problem that we need to be aware of. Be aware of the algorithms we're using, if they are prone to multicollinearity, or if some algorithms have ways of handling that on its own, that we don't have to help the algorithm, but others do not. And so of the models that do not have an inherent way of dealing with this issue, we have to be aware of it so we can help the model to be safeguarded against multicollinearity. And then here on the effect of precipitation in October, we only had two models that included that variable. One of them was the model by itself, where it was just cumulative precipitation October explaining strength, which is this one here. And then the other was precipitation October on the model that it was explaining strength along with May day length in April, which was the two var uncorrelated. So again, two uncorrelated predictor variables, and you see that both when precip was alone in a model or was in a model with another variable but uncorrelated, you still had the very similar estimates of the slope and very similar errors around the estimates. Although, I mean, and really, maybe you would look at this plot and you would say, wow, precipitation October doesn't matter if it's in a model with or without multicollinearity issues, it is highly uncertain. And that's true, right? But I don't want you to focus on comparing the error bars of cumulative precipitation October with the error bars of mean day length and thinking about that way, because it's just, in precip in October is just inherent to that variable that it is more variable. And the variability in precip in October is not coming from multicollinearity problems. It's basically just because it is more variable. Whereas for mean day length in April, we were able to see that if it is in a non-multicollinear model, it has a positive effect to strength, and the error around that estimate of slope is very small. But in a multicollinear model, that changes, right? You have a different interpretation, and also the error around it increases a lot. Okay, I want to take just a quick moment and allow for any questions, because I know we ran different models, different things, so it could be a little bit confusing.
Professor, I have a question.
Yes, go ahead.
So from what I understood so far, if both models show high uncertainty, that means it's because of that variable itself is highly uncertain, just like precipitation.
Yeah, so that is one of the takeaways here, right? So if in this case here it just means that there's more spread around the slope of precip explaining strength than there is around the slope of day length explaining strength. Yeah, it's just that the inherent to the data.
Okay.
Yep.
Thank you.
All right. Any other thoughts or questions before we move on? Okay, so we just have a couple more chunks and then I'll give you a break and then we'll come back and continue. So we notice here that again, on multicollinear models, the direction and the magnitude of your model estimates can change, which is not good, which is not something we want. So, you know, okay, so if you're running all these models, should you then always run a correlation matrix like we did, and then look at everything that's highly correlated, and then maybe remove half of it, and then keep with the rest that is not correlated? Maybe that could be one way. But there is another, well, there's a few different ways that we can use here to make a better decision. One of them is going to be a metric that is the, we're going to use here the variance inflation factor, or VIF, as a metric to guide us to understand if our models are multicollinear or not. So this is going to be a metric that we're going to use to check for multicollinearity. In general, like a general rule of thumb is models that you have a VIF around 1 do not present multicollinearity. They don't have that issue. Values where the variance inflation factor, VIF, is between 1 and 5 have moderate multicollinearity. So maybe, you should perhaps try to address it, but it's probably not like severe to the point of really changing a lot of your interpretations. But if you have VIF values larger than 5, then you have severe multicollinearity. You're probably working with models that are suffering from this. So the estimates of the model, the direction, magnitude, and the error associated with them are probably being impacted. So I want to show here how we can check for the VIF, for the variance inflation factor for our models. The first one here is going to be for our uncorrelated model. So we expect this to have very small VIF value. Let me see here if I can help us a little bit. So if we go, this is the model day length in April and October. So that was our, let's just scroll up to our models. We can just copy the model. I want to copy this one here. So strength explained by mean day length in April and precip in October. You can just copy, like starting in LM and ending right before the pipe. If you copy that, so we don't have to type it. And you scroll back down to the chunk that we were starting to develop, you can just go ahead and paste that. If you just run this, it's basically just that model object itself. I want to pipe this right into a function called VIF. So if you do that, this basically calculates the variance inflation factor for each one of our predictor variables, each one of our X variables. So our predictor here, April, day length in April and precip in October, we see that the VIF value for both of them is close to 1. So this model, as we expected, does not suffer from multicollinearity. And we expected that because we checked the relationship between these predictors and it was pretty much no relationship. Now, if you go to the next chunk, I left you the code so you don't have to do anything besides running it. But this is the model that we did have multicollinearity problems. So the model where we have mean day length in April and May, which we know are highly correlated. If we run that, you're going to see that our VIFs are really high, 64. This is extremely high. So this would be a case where you have another way of saying, okay, this model is suffering from multicollinearity problems. I need to do something to help here. All right, so this is a good stopping point for a break. Let me save my script. I'm going to give you a 5-minute break, and then when you're back, we're going to start playing with principal component analysis. Yes, just a sec. All right, so our break is over, so let's return here. Again, if you're online, please turn on your cameras. All right, so, okay, so we basically determined here that if you have two or more highly correlated predictor variables, X variables on your model, your model will suffer from multicollinearity, which is bad for us because you may learn and interpret a different relationship than what actually is between your X variables and your Y variable. So we don't want to do that. Now, how can we, so let's say you run them up. Yes, Charles.
What if you have three variables or more variables? Is there, can you divide the bias in some way? And you cannot really tell, like, if there's like multiple linearity.
So let me repeat the question for those online. So Charles is asking, what if you have three or more variables in the model? Can VIF identify that relationship or that effect of multicollinearity when you do have more variables? So if we were to keep adding variables here, let's say we added 10 variables, what we would see is you would have so different variables are going to have different levels of multicollinearity. But then when VIF is calculated, it's going to give you a value of VIF for a specific variable, right? And so in this case, we only had two variables, so there's only a correlation between them. So the VIF of both variables was the same. But when you start having more variables, you're going to see the VIF values would be different, right? So for different variables, and basically it shows up almost like in pairs because it's showing us the VIF of that variable with another one that's highly correlated with. And so you would have different VIF values for different variables in models that have more than just two X variables. Yeah, that's a great question. Okay, so if you are running a model, an algorithm that does not have an inherent way of dealing with multicollinearity, which some do, some don't. We're going to talk about these more in machine learning. So, but let's say you're working with a model that does not handle that by itself, but you still would like to use some of these or a lot of variables to explain a given response variable. What can you do? So the first thing that you can do here is dimensionality reduction. And there are basically two ways, I guess, that we can think about that. One of them is dimensionality reduction by hand. What I mean by this is instead of calculating all these variables and just throwing everything against the fan and see what sticks, we basically handpick the variables that you either know from experience or know from the literature that do have an effect on your response variable. So instead of doing a try all out approach, you only pick the X variables that you know have an effect on your response variable. So this would be one approach that is actually highly recommended, that instead of doing these like creating these thousands of predictor variables and just giving all of them to a model and let the model do the work for you, that you do a little bit of that work beforehand and you only give the model variables you truly believe make sense. So a good example in our case here is all these variables that were reflecting weather data outside of the growing season of the crop. Maybe we can remove those variables because we at least don't expect for them to have such a high impact on the crop because the crop was not even growing then. Yes.
Great. I don't know if it's a common practice. I don't know if that's for a ton, but I've driven by fields and I guess after harvest, November, December, I always see huge bales just left out in the field, like a big tarp. I don't know if that's common or maybe that's why it's sitting out in the sun. I don't know.
It's actually a great thought that I had not thought of. That's a really good point. So Zach brought a really, really great point here. So he said that he noticed just by driving by like fields that he would see like cotton bales just sitting by the field waiting to be picked and taken to a gym to be processed. And he was wondering if maybe weather data during the months where the crop is not growing, but maybe the bale is out on the field being exposed to weather, maybe that could have an effect. That's a really great point. And I think it would have some effect, but overall the bayo is protected by a plastic layer that is there for that purpose, to protect it. And also, normally they would not be sitting out for too long. I mean, maybe, I don't know, a couple weeks, maybe a month, depending on how fast they can get them to the gin. So that is a great point. It is really, I like the way you're thinking, because you're thinking of like, okay, maybe there is something outside of the growing season that could be impacting. This is the reason, and I totally agree with you. In our case, I think it would still be a little bit of a stretch, just because I know that this data is coming from small plot trial data, meaning that they probably harvest and already take it for processing. It's not sitting out there just as it would be on a grower's field, potentially be in a grower's field. But that's a really great point. I like the way you're thinking. Awesome. Okay, so then just coming back here, so we could do dimensional reduction, which basically means giving less columns to your model, giving less variables to your model by hand, but we can also do that by math, or by using an algorithm that is going to help us with dimensional reduction. And one of them is going to be principal component analysis. We're going to do an exercise next, so you understand how that works. Another way that could be used with the first set here of dimensional reduction, or could be used by itself, is just using an algorithm that has some way of handling multicollinearity on its own. So some algorithms do variable selection, for example. These algorithms, they already are trying to select variables that are most important, and perhaps they are, because of that, they can be a little bit more robust against multicollinearity. And some models that we're going to see here, one of the first models we're going to learn is a model that is an ensemble of many bivariate models. So even though overall the model is multivariate, but it's built in parts where each part is just a bivariate relationship between X and Y. So that is another way of dealing with multicollinearity, because you're not giving all X variables at once. The model is looking at them separately and choosing the best ones and building the model after that. And again, we're going to see better, or we're going to play with an example that does this, so it becomes more intuitive for you of what I mean with that. All right, so our next thing here is going to be to look into principal component analysis. And one thing that before we get there is I wanna make you aware of this, that is a especially important step in machine learning models. So many of these models that we're going to be using, they use some form of similarity or dissimilarity among the predictor variables, or the X variables. And when that happens, if we do have predictors that have very different magnitudes of measure. So for example, we have here the minimum temperature in January ranges from -10 to 10 Celsius, and the mean day length in July from 48,000 to 51,000. So just the magnitude of the measure of those variables is very different. And if we don't standardize or normalize that, what would happen in some of these models is that variables that have a larger magnitude would have a higher impact on the model, even if they're not the most important variables. It's just an artifact of them having a higher magnitude. And we do not want that to happen either, because we want variables that are truly important to be driving the model, and not just variables that have a higher magnitude, but perhaps are non-important to our response variable. So because of this, we're going to have to normalize that measure, so that the scale or the magnitude of the variable is not what's driving its importance. It's the actual relationship of the variable with our Y variable. So with that, we're going to take all these numerical variables and we'll normalize them by centering and scaling before we start working with multivariate analysis. Some analysis, like in the case of the one we're going to do next, which is principal component analysis, does that for you already, but others do not. So for example, we're going to be looking at a clustering algorithm also called k-means, and k-means does not do that inherently. So just to make sure that we are keeping things normal or standardized here, what I want to do on this next step is, well, let me just take a step back here. So both models, both principal component analysis and k-means, which is going to be the second model that you're going to see, they only work with numerical variables. So what in this step here, because we're getting to PCA, I just want to keep all the numerical variables and give PCA the variables before being standardized. However, when you go into k-means, we will need to standardize the variables as well, so they are centered and scaled. So at this point here, if you come to this next chunk, we're going to create this object called weather n. That is basically going to be weather and give it a pipe. We're just going to select all the predictor variables that are not, or all the predictor variables that are numerical. Basically, what that means, so let's use a dplyr select, is we're going to leave out year. So year is numerical, but I don't want to have in the model because it does not help me to have a predictive model that tells me that in 2010 this happened. I mean, I want a model that can look into the future, right? So I want a model that understands what happened weather-wise in 2010 and look for those patterns in the future instead of telling me 2010 was a year that this happened, right? We're going to remove site as well, and we're going to remove our predicted variable, which is strength. So minus strength underscore gtex. If you run that, well, the object weather n has 72 columns that only contains the columns related to weather. And at this stage, they have not been centered or scaled. They're still on their native scale of measure. Okay, so let's talk about principal component analysis. So PCA is a dimensionality reduction approach that only accommodates numerical variables. So if you have a categorical variable, you're going to have to either drop it or maybe transform into a dummy variable. But right now, our data set only has numerical variables, so we're good there. So what principal component does is going to look for linear relationships of your original variables and represent them in a lower dimension that are the actual principal components. So a couple of things related to this. If you give, so we have 72 predictors. We're going to give 72 predictors to PCA and ask it to calculate all the principal components. The principal components, which we're going to see here in a second, what that means and what they are, the analysis itself is going to give you 72 principal components. So it's going to give you the same number of components as you gave it variables. The key difference here is that if you have variables in your data frame that are highly correlated, the principal components are going to look for those correlations and are going to be able to give the components that themselves represent variability or correlation across many variables. So instead of you needing all of your 72 original variables in a model, maybe you can use 2 or 3 or 4 principal components instead that represent maybe 70, 80, 90% of the variance on your data. That's basically what we're looking for here, is giving all the data, getting principal components back, and maybe requiring fewer components that can explain the majority of the variance of your data of all your 72 variables. So that means that PCA works well when you have many variables and you have some level of correlation between those variables. If you have 1,000 variables, but none of them are correlated, you're basically going to need to have all of your PCs to explain the same amount of variability as you would of just having the original variables. So PCA works well if you have many variables and some of them are highly correlated. And so again, PCA here is used for dimensionality reduction, because instead of using all of the original variables, you can use a subset of principal components based on the original variables that instead. So that is something, that's why it reduces dimensions. It is unsupervised analysis. What I mean by that is we do not have a Y variable. We just have X variables. We're just giving all of our predictor variables and saying, look for correlations here and give me just the PCs that represent some level of variability within this data. So another way of saying that is that it only takes predictors, and those predictors need to be numerical. All right, so some of the properties that principal component analysis has. Again, the number of principal components is the same number of variables as you give it. So if in our case, we're going to give it 72 variables, it's going to give us back 72 principal components. The overall, and where each one of these components is a different linear combination of all of your original variables that you give it. Something very important to understand is that the overall variance explained by each PC will always be highest for the PC number one. So principal component number one is going to be the one that explains the most variance across all of your 72 variables, and then followed by PC2 and PC3 and so on. So it's on a decreasing order, meaning that again, your PC1, principal component number one, is going to explain the most variance of your data, and your last principal component, which in our case is going to be principal component 72, because we have 72 variables, is going to be the one that explains the least variance of your data. So it's always in the decreasing amount. Now, something that's really key about PC that if you were to do dimensional reduction by hand, you would not get this. And PC gives you this, is that all principal components are orthogonal. What does that mean? This means that all principal components are independent of each other. None of them are multicollinear. Even if you give a lot of multicollinear variables to PCA, it's going to give you back principal components where none of them are multicollinear. So this is a very key property of principal component analysis that a lot of times is used in science. So a lot of times what people would do is, you have this data set that has many multicollinear variables. People first run a PCA analysis, extract the principal components, and then train a linear model with the principal components themselves. Because in that case, even if you give all 72 principal components, they're all orthogonal or independent. They have zero correlation between them. So that is a very key property of principal component analysis. And again, because you get back the same number of PCs as how many variables you give the model. The goal here is never to use all the PCs that you get back. The goal is that because the PCs are going to be linear combinations of the original variables in a way that they explain a lot of variance, the goal here is to select maybe 2 or 3 or 4 PCs that will explain a good amount of variability of your data. So normally we have a trade-off. You're never going to select 2 PCs and explain 100% of the variance of our data. That does not happen. The only way you can explain 100% of the variance of our data with PCs is to select all PCs. And in that case, it does not make sense, because if you're going to use all PCs, just use all of your variables, except for the multicollinearity part, which PCs are orthogonal, your variables are not. So our goal is going to be to look for, let's say, this depends on the data set, of course, but the more highly correlated your variables are that you give to PC, the more variability or variance PCs 1, 2, and 3 will explain of the overall data. So a lot of times when you see a principal component analysis graph, it's going to show you PC1 on the x-axis, PC2 on the y-axis, and it's going to tell you what percentage of the data variance is explained by these 2 PCs. So it's like 27%, maybe like always PC1 is the highest. Let's say PC1 is 50% and PC2 is 30%. So with 2 PCs in this fictitious example I just made up, you explain 80% of the variance of your data that you would otherwise need all variables to explain. All right, so I have a little animation here just to show, if you run that chunk, it's just going to show you how PC is working. This is a highly simplified example with 2 dimensions, 2 variables, x and y. We have 72 variables or dimensions. It's impossible for our minds to wrap around that concept. So just in a very simplified way, on a 2-dimensional principal component analysis, this is what's doing. So on the first step, well, let me just wait for that to loop back to step 1. Okay, so the first step is standardizes the data, so it centers and scales, and then it looks for which direction of these two dimensions it's gonna draw the first PC, which is the one that will be in the direction of the highest correlation or the highest spread of data. Which you would notice that is, so on that cloud of points, the high direction that had the most variance is the one going straight up, and the second direction that had the most correlation is the one going perpendicular to that. So then the PC1 becomes this, and PC2 becomes this direction. So these are the eigenvectors being calculated. The eigenvectors are basically the direction of those PCs, and the longer is that eigenvector, the more important that PC or that variable is for that PC. After it calculates that, it gives us back the eigenvectors and gives us the principal components as well. And we get a lot of information about how much variance is explained by each one of the components, and what are the loads or the weights that each one of your original variables have on each PC. So let's apply that to our data, and I think it's going to perhaps be a little bit easier to understand what's going on here.
Dr. Bestos.
Yes.
So if I run the chunk for the GIF, it's not running for me. I don't know if it's just only me.
Not running. Okay. So it seems like it's not running for a lot of you. If you copy this address and just paste on your browser, does that run? Because I wonder if it's a link problem or if it's a function problem.
Yeah, it's runs.
Okay, so maybe it's something with the function itself. Well, I don't want to spend time figuring that out, but we can, if you want to open an issue on GitHub, then we can maybe, as a group, look for a solution. It's probably related to the package knit-r and the function include graphics then. Okay, so let's go ahead and run our PC here. So the first thing that we're going to do is use a function that is called prcomp, or principal components. We just give here our data, which is the one that we created above, weather_n, that just has the numerical variables of interest. And then it has an argument for scale. So scale dot, we want to say true. So this is where the PCA function is doing the scaling for us before it runs the analysis. Let's just go ahead and run it. It goes pretty fast, so it's not a very heavy algorithm to run. And let's just print modPCA here so we can take a look. So it has a lot of things going on, but what I want to show you a couple of them here. So the first one is the following. Although you're not going to be seeing on this screen, at least, the full nature of it, but each PC, so PC1 is the first one showing up here. What you're going to see is that each one of our 72 original variables has a weight, and this is the eigenload or the load vector for this principal component one. Each variable has a load on this PC. Each one of these loads is just a weight that each one of those variables is receiving when representing principal component number one. So principal component number one is a linear combination of 72 loads or weights, one for each variable. So normally when we say that we do dimensionality reduction, it's not that PC is really selecting variables for you and saying, just choose these ones. The PC analysis is actually using all of your variables for all of the PCs. It's just that you may select a fewer number of PCs to then continue the analysis if you do a regression afterwards, for example. But each PC is going to have a load for each one of your variables, and each PC is going to have a linear combination of all those loads to represent that PC. And the way that those loads happen is basically looking at all those 72 directions, doing your eigenvector for PC1 on the direction that has the most variance, and then estimating what would be the estimate weight for each one of your original variables to represent that eigenvector. Just going to scroll down here. I think there may be a lot of scrolling. But basically, that's what we have. For all the 72 PCs, we get 72 PCs back, and each one of them is a linear combination of weights for each of your original variables. Now, again, the goal is for you to run PC, but to choose a subset or a smaller number of PCs than original variables to continue your analysis. Then the question that you may have is, how do we do that? So how would you choose, how do you know how many PCs you need to continue any given analysis? We're going to do a plot that's called scree plots. So the function we're going to use is called fvis underscore eig for eigenvector. We're going to give the model name, which is mod underscore PCA, and we're going to say change the argument add labels to be equals to true. So if you run this, we get the scree plot, which for us is just showing the first 10 PCs. Remember, we have 72 PCs. We have the same number of PCs as variables. But it's showing us here the percentage of the explained variance for each one of the PCs. We see here that PC number 1 explains 35% of the variance of the entire data set. PC number 2, 26%, PC 3, 7%, and so on. It will always look like this. PC1 will always explain the most variance, and that decreases until your last PC. And again, in this plot, we're just showing the first 10 PCs, but we have 72 PCs that could keep going on this plot here to the right. So let's say one way that you could determine how many PCs you want to continue to use in further analysis would be, well, my rule is I want to explain at least an X% of variance of my data. So maybe that's your rule. If you have a rule of I want to explain at least 70% or 80% of the variance, then you need to check how many PCs you need to reach the level, and that those are how many you continue your analysis with. So let's say if I wanted to use enough PCs to explain 70% of our total variance, how many would we need? There's a different ways of doing this. I want to show you a graphical way of assessing this. So let's call our model mod underscore PCA. I want to pipe that into a function called get underscore eig. So we get the eigenvectors. So notice here that we have eigenvalue in different dimensions. We have 72 rows, 72 dimensions, where each one of them is a different variable. And then we have our eigenvalues with the variance and the cumulative variance percent. So basically, so these are actually your 72 PCs, not variables, as I said before, so my apologies. So these are your 72 PCs where we know how much variance each one of them is explaining and what is the cumulative variance. So if you add the first to the second to the third, right, that would be your cumulative. So we can go ahead and make a plot here. So I want to pipe this into a mutate. I just want to give a PC number, which right now we don't fully have that. So I want to call this function PC and say that this is equals to 1 colon n row. And this, if we just run that, is going to create a column for us with basically called PC going from 1 to 72, just so we have an ID of the principal components. Then I want to pipe this into a ggplot where on the AES, on the x-axis, I want to have the PC column, so the number of the PC. On the y-axis, I want to have this cumulative dot variance dot percent. Then we add a plus. I want to add a geom bar. So we have a bar for each one of those cumulative variance explained by each PC. We need to say here inside of it is stat equals to identity. So it works properly. If you run this, this is what you give. This is what you get. So as you're seeing, this is the cumulative, right? So this is the cumulative explained variance. So you see that the first PC here in this case by itself is explaining 35 or so. And then we keep adding how much each other PC adds here. And you can see that you can only get 100% of the variance explained if you get all 72 PCs, which is not what we're doing here. It's not the goal. So let's say that I wanted to achieve at least 70% of the variance explained in this data set. We can add a geom age line for a horizontal line. It has an argument for y-intercept. We can say equals to 70. So we're going to have a horizontal line here cutting through at the 70% cumulative variance explained. So in this case here, you see that where the line crosses, the first PC that goes above that line is 1, 2, 3, 4. So we would need 4 PCs to explain at least 70% of the variance of all 72 variables. So this would be a visual way of us assessing how many we would have. So this threshold of 70%, I mean, some people may want to do 80, some people may want to do 90, some people are maybe okay with 60. So it's a subjective number. And normally people really are focused on the first 3 because it's going to be easier for you to explain things with the first 3. And they're the ones that are going to have the highest proportion individually. So that could also be a way that you make the decision here. All right, so now let's inspect our principal components. We're gonna check the loadings or the weights of each variable towards each component. Sometimes, in our case, it may be a little bit difficult, but sometimes you may want to see what are the loads of each variable towards the most important PCs, so you can try to interpret that PC. You may be able to, looking at the weights of the variables, you may be able to say, well, PC1 here, I see that, well, I guess before I say that and make up something, we can just look at the data and interpret what we truly have. So I left you the code here. I think I left you all the code. Well, what we're doing is basically getting the rotation from our PC model, transforming that to a data frame, turning our rows to columns like this. So I know exactly the weight of each one of my 72 variables for each PC. And I'm basically making a ggplot to show that. So you can take a look in the code on your own later. I just want to run it so we can look at this. So here for PC1 only, this is just PC1, we have the weights or the loads for each variable on the x-axis, and I order them from highest to lowest. So what we see here is if we were trying to interpret what is PC1, what is it related? So I see that PC1 has high positive weights for variables that are related to day length. So day length in January, December, February, October, and March. So the first 5 highest loads for PC1 are all day length related. And if I look on the other side of this, so on the most negative loadings here, we have mean day length in January, June, May, August, April. Okay, so for PC1 specifically, if we look at the highest loads, both on the positive and the negative side, they're all related to day length. So maybe we can find some interpretation of this. So of those day length variables, both on the high PC and or on the high loads and the negative load side, do you notice any patterns there as far as what are those variables and which ones are on the positive, which ones are on the negative side? So on the positive side, just I can help you in case you're not being able to see well. We have day length in January, December, February, November, and October. And on the negative side, we have day length in July, June, May, August, and April, September. It looks like a seasonality type of thing, right? Where we have day length in the winter pretty much versus day length in the summer. So maybe it's a seasonality type of interpretation that we could have out of PC1. Now, this is, if you can find those patterns when you're looking at the loads of variables for each PC, great. Then perhaps you can give them some interpretation. But sometimes it may not make a lot of sense, and maybe you're not able to interpret what what the loads of a given PC are telling you, and that's fine. I guess in this case here, we can kind of perhaps create some interpretation that PC1 is related to seasonality, perhaps, because it has the high loads and the low loads are all the same variable in different seasons. And just to show you here, so we showed for PC1. So let me just change this code and show you for PC2, perhaps. So if you show for PC2 instead, well, and I also have to change here. So I changed PC2 on the X and on the Y. So make sure you change on both. So now we have a different set of variables, most likely, with different loads as well. And this is now PC2. So PC2, on the high loading side, we have vapor pressure deficit in June, May, July, August. And on the low side, we have solar radiation in May, June, July, and so on. So again, each of your PCs has a weight, has a load for all variables you give the analysis. And the importance of which variables are driving that PC, you can inspect with the loads. And you can see which direction they're going as well. So this is how we could use the loads to try to at least interpret each one of our PCs. All right, so if we return to talk about PC1, because again, PC1 will always be the most important one, the one that explains the most variability. And I want to understand which variables contributed mostly to PC1, regardless of the direction. So regardless if it is a positive or a negative load. If you come here to this chunk, we're going to use a function called fvis underscore contrib. We're going to give the model, so mod PCA. It has an argument for choice. We're going to say choice equals var. And we're going to say axis equals 1. If you want to know more about these arguments, you can check the documentation of this function. But I just want to run that and show you. So this is basically just showing us for PC1 again, all the variables in an absolute term. So regardless if it was positive or a negative value, it's just looking at the absolute value of that load and just showing their importance. So if we check here, we just take a closer look at this plot, we see again that all the first 8 variables that have the highest loads for PC1 are day length related. And this dashed line here is just showing you the average contribution of each variable to this PC. So maybe you could, if you wanted to use the average contribution to then look at which variables are contributing more than the average, you could do this and perhaps use that as a guideline of which variables you want to use to interpret this PC, perhaps. So this plot is just a different way of looking at the plot above. It's just taking the absolute contribution rather than on the plot above, checking if it is a positive relationship or a negative relationship. Okay, so the next thing here is we're going to look at the eigenvectors for both PC1 and 2. This is a very common thing to do, is you would get the eigenvectors for both PCs and do a scatter plot of that. Or I guess in this case, it's not just a scatter plot, it's more a plot where you have PC1 on the x-axis explaining 35%, PC2 on the y-axis explaining 26%, and then each arrow here is one of those arrows we saw on the animation, where it is basically driving this arrow for all of our 72 variables and adding their names here, which gets really busy, right? So it's really difficult for us to really make a lot of sense of this. But basically, one way that we can interpret this plot is each 2 arrows that are in opposite directions, especially if they are exactly on going in different directions, we could say that those 2 variables are inversely related when explained through PCs 1 and 2. So we cannot really tell which ones they are, but this arrow here, whatever variable that is pretty much in opposition to this other arrow. So those two variables, whichever two they are, they're inversely related in relation to PC1 and PC2. So we can get some understanding of that as well. And the longer is this arrow, the more important that specific variable is for that PC. Okay, so the next thing that I want to do here is look at the scores. So what is a score? So we have the eigenvector, which is basically this vector here showing the importance of each variable, in this case in 2 dimensions in 2 PCs. We have the loads or the weights, which are the weights of each one of those variables towards a given PC. And then we have the scores. The scores is basically if you take, so imagine that, let me show you here, coming back very quickly here. Or maybe to one of the plots, I think it's an easier way. If I just look at, yeah, this plot here will work. So if I just run the data before getting to the plot. So PC1, we have all these weights. All 72 weights for all 72 variables. Now imagine you take your first side year that you have an actual value of mean day length in January, solar radiation, and so on. You have an actual measured value for each one of these variables. You just multiply each one of those actual weather data values by these weights. And you do that on this linear combination for all 72 variables on a way that you would do, let's say PC1 equals to mean day length in January times 0.17 plus mean solar radiation January times 0.06 and so on, and do that for all 72 variables, and you do that math, in the end you get one value for that side year, one PC1 value for that side year. That's what the score is. And the next plot we're going to explore here is the score plot. So if you come here, we're going to use a function called fthis underscore PCA underscore int for individual. We give mod underscore PCA, and let's say label equals false. So it's a little bit easier to see. So this is the score plot. So this is basically for PC1 and PC2, taking all those weights and multiplying those weights for all variables for each one of our side years, we get the scores. So each point here is a side year for PC1 and PC2. This is a very popular plot in PC analysis as well, because it helps you to show basically 2 PCs, which in this case represent 56% of the variance of the entire data set in 2 dimensions. So here, just looking at here, maybe even with the caveat that we're only explaining 50 or about 60% of the variance of the data set with both PCs 1 and 2, you can perhaps identify some clusters, some groups here, just visually, right? And this can be useful for you. Maybe that is also a way that you want to use this, is to maybe find side years that are similar in 72 dimensions, but it's hard for us to see that. So PC helps us to visualize that like this. Okay, so it looks like we may have some groups, and we're going to explore that in the k-means exercise. But just to wrap things up here on the PC side, so we checked in the beginning of this exercise that some of the original variables are strongly correlated. So we would expect then, because of that we would have PCs 1 and 2 that when combined would explain a good amount of the variance of the data sets. Again, if you give PCA a lot of predictors and they're poorly correlated between themselves, PC is not going to be very useful, because you're going to say, well, PC1 is explaining 10%, and then PC2, 5%, and so on. So it's not very helpful if your original data does not have high correlation among the X variables. In our case, we saw that if we wanted to explain at least 70% of the original variance of the data, we would need at least 4 PCs. This changes is specific to each data set. And here we saw that for PC1, the most important variables were related to day length in the winter and summer months. So perhaps PC1 has some explanation or interpretation related to seasonality. All right, so I have a few chunks here that I think we can get through at least some of them now. That is going to be to wrap up the PCA and the usefulness of PCA. I see we have 6 minutes left. I do want to tell you that even if we need more time, maybe we're going to take another 5 minutes. Today, I'm going to make the decision of taking those extra 5 minutes and going through. If you have to leave, you're welcome to leave at the class time. I would just ask that you watch the last 5 minutes online on your side as well. So if you have to leave at 11:30, you're welcome to do that. But I think for sake of continuity, it's going to be more useful for me to extend 5 minutes today to complete this exercise. All right, so I told you that one of the features of PCA is that each PC is orthogonal or independent or non-multicollinear with every other PC. So I want to actually test that and show you that in reality. So let's first extract our 4 PCs and then first let's just do that, and then we're going to join them into our original data sets. So on this chunk, let's just extract the first 4 PCs. So let's give it the assignment symbol. We're going to call the mod PCA object. We're going to use the $sign to go inside of that. And one of the things we can extract from it is X. So X is just the matrix of our PCs. So we can just print that. You can see it's just a matrix that has all the loadings for all the PCs. I want to transform this into a data frame. So let's use as data frame. So that transforms this into a data frame for us. And then we're going to use dplyr to only select the first 4. So dplyr select, let's just do PC1 : PC4 to only get the first 4 PCs. And what we're seeing, these are these scores. So the reason why we have 698 rows is because we have a score for each of the 4 PCs for each side year, which again is basically derived by, for that side year, taking all those weather variables and their actual values, multiplying them by each one of the weights for that variable in that PC, and just adding up in the end all the results. So this is the weight for PC1 for the first side year. This is called the score. All right, so now I want to add those first 4 PCs to our original data frame. So if you go on the next chunk, we're gonna call here weather, which is our original data frame containing side and year. And then we're just gonna use a function called bind cols. So this is gonna bind the columns of this PCA scores with our original data set. So bind cols of PCA scores. If you run that and you just print weather post PCA, is basically our original data set. And if you were to scroll all the way to the right, you would see 4 PCs. Right there. All right. So now I want to run a multivariate linear model here, where we're going to use the function lm, just like we were using before. I want to explain strength as our response variable. So it's strength in GTEX explained by PC1 plus PC2 plus PC3 plus PC4. And then we just say that the data equals to the object that we just created above, weather post PCA. If you run that and we check the summary, we are basically getting, let me just leave it here. We're basically getting an estimate for the slope of the relationship between each one of the PCs and strength. So if you notice, this is a multivariate model where instead of giving the original weather variables, we're giving the first 4 PCs. And we see here that PC2 and 3 are statistically significantly explaining strength, whereas PCs 1 and 4 are not. Before we further explore that analysis, I want to check the variance inflation factor of this model. So let's call VIF of LM underscore PCA, which is the object we just created above. And look at that. Our VIFs are all 1. This is, again, one of the key advantages of principal component analysis. So all of your PCs are orthogonal. If you were to include all 72 PCs in this model, they would all have a VIF of 1. That is a property of PCA. If you were to include all 72 weather variables, as you already saw with only 2 of them, we're going to have multicollinearity issues. So this is one of the main benefits of why we use PCA, is to have orthogonal or independent PCs. Okay, we have a few more chunks here that we can get through. So I want to just plot strength versus PC1, just so we understand why PC1 is not explaining strength. Just visually assessing that relationship. Let's use ggplots. We're gonna call our data weather post PCA. That's the object that we had above. On the AES, on the X, I want to put PC1. On the Y, I want to put strength in grams per tex. Then we're going to add a geom point. So if we just run that, this is what we see. And just to make sure we understand why the p-value of PC1 was not significant for strength, we can add a geom smooth with method equals LM, just to visualize it as well. There we go. So strength on the y-axis, PC1 on the x-axis, we can really see why PC1 is non-significant in explaining strength, as we saw in the summary of this model when we ran it. There's no relationship here between PC1 and strength. Remember, we did not give strength to PCA. PCA did not see strength. They only saw weather variables. All right, so let's do the same with PC2, which we know PC2 was significantly related to strength. So I left you all the code, you just have to run it. So we see that there is a positive relationship here. If you were to go back to the summary function of this model, we would see that the slope of PC2 is greater than 0, so it's a positive relationship. And we see that it has an effect on strength, even though it's still very noisy. There's still a lot of noise around that. And then finally, we're going to do the same for PC3. So if you just run the code I already left you, we see that PC3 is actually inversely related to strength. Something we can think about as well here, going back to PC1, if you remember PC1, the main variables, the variables that had the highest loads on PC1 were day length, especially inversely the ones in the summer versus in the winter. So maybe day length in summer versus winter is not very important in explaining strength. Maybe that's one interpretation you can bring back here when you're using the PCs to explain your response variable. All right, so that basically wraps up this exercise. So we saw here, we understood why PCs2 or how PCs2 and 3 were explaining strength. Right, so we saw that on that linear model, PCs 2 and 3 were significantly affecting strength, and then we plotted that to kind of have an understanding of why that was. And as expected, all the 4 PCs were non-multicollinear. They had a VIF of exactly 1, and this is a feature of PCA. A lot of times people use it this way. You have a lot of a lot of variables. You just run them through first a PCA analysis, get the PC scores out of it, and then continue your further analysis using the PC scores rather than the original variables. And so in summary, in this exercise, we covered when we use multivariate analysis, how multicollinearity can be an issue and how to fix it. We then implemented PCA for dimensionality reduction in our data set. We saw we would need about 4 PCs to explain 70% of the variability. And then we validated some of the PCA results and checked especially that they were non-multicollinear as we would expect. So this wraps up this exercise. Before we head out, I want to tell you that I have an exercise for k-means, which is basically follows this. But because I want to get to machine learning algorithms and training faster, I'm going to have the k-means as a assignment for you to do. So you're going to have to watch a 15-minute video, code along in class, and then answer some questions on the assignment. It's pretty straightforward. And I think I'm sure you can do that on your side. If you have trouble, questions, issues, make sure to post on GitHub so others can help you. And I just posted that assignment today. I think I have on the assignment, I said that the due date is next Tuesday, but I want to give you a full week. So it's going to be on next Thursday. So for you to do the k-means on your side. All right, I think Raminder has the attendance issue open. So if you have not yet, please go ahead and claim your attendance. I know we're over time today, 5 minutes. I apologize for that, but I think that was for benefit as well for continuity here. If you have any questions for me, I'm going to be around for a few more minutes. And if not, make sure you claim your attendance and you're dismissed. Yes.
I just wonder, when should we expect the term?
Yeah, so I'm going to grade them tomorrow. I mean, finish grading them tomorrow. Yeah. So by tomorrow, I want to have your grades posted. Yeah.
Dr. Basis,
Yes.
I have a question, like, how do we